Hello. So, little quick video about the basics of rotational dynamics or rotational kinematics and such. So, to start, I want you to imagine that we have a wheel. Wow, look at how good that wheel is. It's amazing. We'll make a little center of the wheel. Well, that didn't work as well. We'll make little spokes for the wheel. Okay, so we have this wheel. Just for funsies, I'm gonna just put a dot on the wheel so we can keep track of that point, okay? So imagine that this is initial. The wheel looks like this. And then in the final scenario, we have the same wheel, but in this final scenario, the wheel has rotated. Okay, so here in the final, the wheel has rotated. So the question is, how far did the wheel go, right? If all it did was rotate, so it's fixed axis. So this wheel, its change in position was zero, right? If it's on a fixed axis, it didn't actually translate or move from one position to another position. So its position hasn't changed, displacement of zero. Its velocity would also be zero. Its acceleration is zero. Its momentum is zero. And its kinetic energy is zero, right? All of these factors are zero for this object because it hasn't actually moved from one place to another. The wheel itself is in exactly the same position in, uh, its larger frame of reference. But obviously, this is like a logical fallacy because the wheel is moving. It just isn't changing its position as a whole, as a macroscopic object, right? So this is illustrating the translational or the linear, right? The larger space movement. And comparatively speaking, describing the rotational. So what this little example illustrates is that there are really two different ways that we could describe the motion of an object, right? An object that is translating, moving from point A to point B in larger space, changing its position, or an object that is rotating. In other words, it's not changing its position in the greater frame of reference, it's merely turning in a single point. So in this case, there must be equivalent quantities to what our translational analogs would be. In other words, like this hasn't changed its actual position at all, but something has changed, right? And in this case, the thing that has changed is really the angle, right, that the object has rotated. So we don't have a change in position or a displacement, we have a change in angle or a change in theta relative to that initial position. If we were to define, say, this initial position, theta naught equals 0, then this is now theta equals the full circle, which would be 2 pi radians divided by, what do I have here? 8 radians. Right? So we could say this object has rotated a total amount of 2 pi over 8 radians as an angle of rotation. So what we're doing here is we're drawing an analogy between physical displacement and rotational displacement. In other words, this term here, the change in theta, is what we would call rotational displacement. Okay, so that rotational displacement is not a change in position, it's a change in angle. Relative again to a frame of reference. So you have to define what angle 0 would be, and positive and negative direction of that angle, et cetera, et cetera. Now, if we could have an analog for rotational displacement, analogous to translational displacement, then there must also be analogs for all of these other values, right? So for example, if there's translational displacement and translational velocity, then there should be rotational displacement and rotational velocity. So there's a rotational analog that is omega, a lowercase omega, and that would be rotational velocity. Note, this is not a W, it's an omega. Note that these are also referred to as, instead of rotational, they could also be referred to as angular. So this could be rotational displacement or angular displacement, rotational velocity or angular velocity. Similarly, there would be a rotational analog of acceleration. That would be alpha. Kind of looks like an A, not an A. Also not a Jesus fish. So that's alpha. That would be rotational acceleration. If there's translational momentum, there must be some rotational equivalent as well. That's a capital L. That would be rotational momentum. And lastly, if there's translational kinetic energy, there's also a rotational kinetic energy. That's K sub R. So this is rotational kinetic energy. And this is just kinematics right here. Okay, so all this is just the kinematics piece. So we could make a table, right? Translational and rotational. Actually, this time I'll call it angular, just so we can have some experience with both of these terms. And then on the left here, I'll have it be the term. So this is position. Translational is x, angular is theta. Velocity. Translational is v, angular is omega. Acceleration. Translational is alpha. I'm sorry. Woo! Translational is a, angular is alpha. We could have momentum. That would be P for translational and L for angular. And then we have kinetic energy. That's K and KR. Okay, so here's the good news. We don't have to actually learn new stuff to understand angular or rotational motion. We're just going to apply everything that we already know about translational or linear stuff to rotation. It works exactly the same way. The only difference is that we have these analogs that we're working with instead of their translational counterparts. So what do I mean by that? I mean that for each of these terms, you can define them the same way for translational and rotational, just with different symbols. Translational and angular. So translational, we had displacement. Displacement. For translational, that was change in position. Well, angular is going to be change in angular position. So delta theta. Hey, cool. how much did the angular position change? We have velocity. So translational, that was v, and v was defined as delta x over t. Angular, we have omega, and omega is going to be defined the same way, except with the angular analogs. So instead of change in position over time or displacement over time, we would have change in angle over time or angular displacement over time. Angular velocity is the rate of change in the angle that is rotated. Acceleration, translationally, acceleration was equal to change in velocity over time. Well, rotationally or angularly, alpha is going to be equal to the change in the angular velocity over time. So this is the basics of kinematics for angular. It works exactly the same way as translational, just we have these different descriptors of the motion itself. So instead of defining position as a change in location, we're describing position as a change in angle. We'll save, we'll hold off on momentum and energy for a short while. We'll get to that later next week. So these things are all true. Now, we could also apply kinematics equations to this as well. So translational and rotational. So translationally, we had the equation delta x equals 1/2 at squared plus v naught t. Well, rotationally, the same relationships are true, just with their rotational analogs. So the angle that an object rotates through will be equal to 1/2 the angular acceleration times t squared plus the initial rotational velocity, angular velocity times t. Similarly, we could have the final velocity is equal to the initial velocity plus a times t. Angularly, that would be the final rotational velocity is equal to the initial rotational velocity plus alpha times t. And lastly, we have our no time equation, which was v squared equals v naught squared plus 2a delta x. Again, there's a rotational analog for that. Omega squared equals omega naught squared plus 2 alpha delta theta. So these things all hold true. So if I wanted to know, like an object that is spinning and it speeds up as it spins, well, that speeding up as it spins, the increase in rotational velocity would be an angular acceleration. The longer that acceleration is applied for, the larger my final angular speed will be. Pretty straightforward stuff. So again, we're not trying to relearn all of kinematics. We're just trying to reframe it in a different context here. Now, you also might remember that we had calculus relationships as well. And just like the kinematics algebraic relationships hold true, calculus relationships hold true as well. So we had translational and rotational. Translationally, we had v equals dx over dt, and delta x equals the integral of v dt. Rotationally, analogs hold true. Omega is equal to d theta over dt, and delta omega is equal to the integral of omega delta theta equals the integral of omega dt, right? Same relationships hold true. We have acceleration was the derivative of velocity with respect to time, and change in velocity was the integral of acceleration times dt. Rotationally, again, hold true. So alpha, the rotational acceleration, is the rate of change of the rotational velocity with respect to time. And delta omega, the change in rotational velocity, can be defined as the integral of alpha dt. So all these relationships still hold true. And that's the basics of rotational kinematics and how you get there. It's really the same thing that we talked about before, except applied to a new situation, new context. So we're going to take this first image, we're going to steal it and copy it. So moving on, how do you get from one to the other, right? So let's say I know I have this object, and this object is rotating, right, like a wheel, but this wheel's no longer fixed in place. So now let's say that this wheel is actually moving, right? So it's the wheel of a car, and the car actually goes from point A all the way over here to point B. So the car has moved as its wheel has turned. So in this case, how do you relate the two, right? Well, consider this, that as the wheel turns, this arc length here is the actual distance covered by the point on the outside of that wheel. And every point on the wheel must cover the same distance because the wheel turns as one single object. And so the difference in the position of the object as it moves from point A to point B, its actual change in position is going to be equal to the arc length of the rotated angle. Right? So if you imagine like this bottom point right here, as this car wheel rotates, that bottom point's going to move this much. Well, the point underneath the car has to move forward, and so it moves forward by that much as well. Which is to say that delta x equal to the arc length would be calculated as the radius times the angle theta. So in order to convert between rotational and translational, you just multiply the rotational component by the radius, given that you are in radians, not degrees. So delta x is the same thing as r times theta. Delta v would be the same thing as r times omega. And delta A would be the same thing as, R times alpha. So again, easy way to convert between the two. Just multiply the angular component by the radius, and you're given the translational equivalent of that.